talk about the estimation maximization, or EM algorithm. Okay, and I'm going to illustrate this with an example. Most of the content in this video was taken from the internet, so you can find the sources I think are cited whenever they were used, and you can go deeper into this by visiting those sources. Now, I'm going to illustrate this with an example. Let's say you have two cases, and each of these cases or conditions have a success or failure. So for example, you have two marketing campaigns in one city, and you have a buyer's outcome or something, and then you want to determine whether that outcome came from campaign A or campaign B, right? And the outcome is whether campaign A succeeded, campaign B did not succeed. Let's say you have two treatments, two medical treatments, right? And you want to see the rate of recovery, right? So, with treatment A, a number of patients recovered. With treatment B, a different number of patients recovered. But you don't know that. You just see the patients that have recovered in different instances, right? So then you can, what you would like to see is, well, which patients were given, which of these recoveries is due to treatment A and which are due to treatment B, which sets. You want to see any other case where there's two conditions, and conditions can be success or failure. This is better illustrated with, or traditionally illustrated with, two coins. Say you have two coins, A and B, okay? One of these coins, say A for example, is more likely to give you to turn heads when you toss the coin. The other one is more likely to fall tails. Okay, so they're imbalanced coins, right? And the thing is, if I pick a coin at random and I toss it, which coin was it? How can I know? By, say, I toss one coin several times, and it gives me a certain percentage of heads and a certain percentage of tails. Can I know whether this was coin A or coin B, right? So this is similar again to saying, I have two marketing campaigns, and I pick one buyer, right? And he buys the product, doesn't buy the product, and then on 10 purchases, there's so many of those 10 purchases in which the customer buys the product, and a few others in which the customer doesn't. It's very similar to flipping a coin. In some instances, it falls on heads. In some instances, it falls on tails. So all these examples of two conditions or several conditions with success and failure outcomes are traditionally illustrated with coin tosses. So I'm going to do the same. Here's the problem. You have two coins. One's more likely than the other to turn up heads. I pick a coin, I toss it several times. Now, which coin did I pick? That's what you don't know. That's what you're trying to determine. Okay, so we're going to do, like I said, we're going to do this 5 times. We're going to try and do this 5 times. And this, most of the material in this tutorial was taken from Kong Do and Serafin Batzoglu. They have a tutorial online. Now, let's do this 5 times. We'll pick a coin randomly, we'll toss it 10 times, and we'll count how many heads and how many tails were in the 10 tosses. Then we'll get the average number of heads for each coin, okay? And we're going to do this 5 times, and that's going to be my evidence. This is the customer data that I see. This is the patient data that I see. So it goes like this, right? So I picked coin A, for example. I picked coin B, for example, and I toss it 10 times, and it falls head, tails, 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 heads, heads, tails, heads, tails, heads, right? So 5 heads and 5 tails. I picked coin A, and I tossed it 10 times, and it gave me 9 heads and 1 tail. I picked coin A again. So randomly, I was picking these coins. Now I know which coins I picked, right? So then what I do here is I count for A, right? For A, I just count the number of heads divided by the number of heads and tails, and that gives me 0.8. For coin B, I do the same thing, and it gives me 0.45, right? So that is basically how I obtain the average number of heads that coin A and coin B can give me, right? So again, it's 24 heads and 6 tails. So to compute the rate of heads that coin A gives me is 24 divided by 24 plus 6. So it's the number of heads divided by total number of heads and tails, and that gives me 80% of the tosses are gonna have 80% of the tosses are gonna fall on the head side. I did the same for coin B, and I can compute it. This is very easy. I know which coins I picked, so I can compute the average for each of these cases. So what if we're giving only the result of our coin tosses? So we're only given, say, the patient data, but we don't know which treatment each patient was exposed to. What if they give us the buyer's behavior, but they did say 5 buyers with different behaviors, but they didn't tell us which marketing strategy they were under, right? What if they give us, again, only the results of our coin tosses? Can we guess the percentage of heads that each coin yields? And moreover, can we guess which coin was picked for each of these 10 coin tosses? One way to think about this is let's do this iterative process. Let's assign a random average to both coins. So let's assume, coin A has 60% heads and coin B has 55% heads, and that is completely random. I just made up those numbers. And then what we're going to do iteratively is for each of the 5 rounds of 10 coin tosses, we're going to check the percentage of heads. We're going to find the probability of it coming from each coin. So basically we're going to, if we think, that the coin A has a 60% probability of falling on heads, right? Then I can see, well, if one round of the 10 coin tosses turns up about 60% heads, then I would think it's from coin 1, right? It would make sense. So with a technique similar to that, we're going to try to find the probability of this round of 10 coin tosses. We're going to find the probability that it came from coin A or coin B, given the random averages that I assign. Then we will compute the expected number of heads using that probability as a weight, and we'll multiply it by the number of heads. This might be a little cumbersome and not understandable yet, but I will explain later. But this is basically, we're going to try to say, well, if I think that coin A turns up 60% of the times heads, and I have this 10 coin tosses, well, what if it were coin A, what would be the probability that it comes from coin A? And what would be the expected number of heads that I would have expected from this coin? I will explain how to compute that. Then we'll record those numbers, and with those numbers, I will recompute new means for coin A and coin B. So with that, then I'll go back to step number 2. Go revisit the 5 rounds of 10 coin tosses, check the percentages of heads, and so on and so forth. This seems like I'm doing the same thing in circles, but really it will be converging to the actual means, to the actual proportions of heads for coin A and B. You will see that these numbers, this is not circular. This thing is actually changing a little bit. And the key to the change is in this middle step here. Okay? Computing the expected number of heads. Okay? This is the key to the change, to the convergence to the actual real proportion of heads for coin A and coin B. First, we need to know a little bit about coin tosses, okay? Because for that key step that I mentioned, we're going to use what's called a probability distribution, and this sounds like a hard term to grasp, but it is not. And I want to explain that very quickly here. So let's see, how do coin tosses behave? Coin tosses behave like this. If I have one coin, let's focus on this example over here. Okay, if I have one coin and I toss it, right? One time is going to fall. There's the probability that it falls on tails, which is 0 heads. These numbers at the bottom indicates the number of heads. 0 heads. There's one case in which it will do that, and the number of heads. Well, I can toss it and it can fall on heads, right? So there's also one possibility that it has one head, right? That it falls on heads. This is basically, as you see, these are two squares. This 50% that it has no heads, 50% that it falls on heads, if I have one tossed. Now, if I flip two coins, right, I can get, for example, the first coin heads, the second coin heads, or the first coin heads, the second coin tails, or the first coin tails, the second coil's head, or both falling on tails. Right? So if we count, if those are my possibilities, and if we count how many coin of these coin tosses that I can possibly do, how many coin tosses can have 0 heads in them? Only one, the case in which I toss the two coins and they both fail on tails. How many cases of my coin tosses can I have where there's 2 heads? Well, also one. The case in which I toss the first coin and its heads and the second coin and its heads, right? So then I saw 2 heads in my flipping of 2 coins. Now, what's the case in which I can see 1 head in this flip? Well, there's 2 cases. When the first coin falls on heads and the second one on tails, or when the first one falls on tails and the second one falls on heads. There's 2 cases in which I can see one head, right? So to recap now, if we look at these probabilities, there's 25% chance that I will get no heads, 25% chance that I will get 1 head, and 50% chance that I will see 1 head. 2 heads, here, 25% chance that I see 2 heads. Now, if I flip 3 coins, the combinations are a few more, right? I can have the first one fall heads, the second one tails, the third one tails, the first one fall heads, the second heads, the third one tails, and so on and so forth, all combinations, right? If I analyze these combinations, I can see that there's one chance in which I get no heads, which is where the 3 coins fall tails, and there's one chance in which I see 3 heads, in which all 3 coins fall heads. And there's equal number of chances that I see 1 head or 2 heads, and so on and so forth. If I do this for 5 coins, this is what it's looking like, right? This is what my counts are looking like. And you can see that this starts forming a curve, right? Like a bell-shaped curve here, right? In the larger the number of coins that I toss. And interestingly, if I toss 5 coins, for example, in this 5, and I think that the coins are balanced, so there's 50% chance of getting heads and tails, right? 50% chance. Then if I toss 5 coins, well, 50% of 5 is, between 2 and 3. And the vast majorities of heads, the vast majorities of trials, I will see 2 or 3 heads. This is what this graph is indicating. This is how the coin toss behaves. Now, this is called a binomial distribution. Okay, many cases with success or failure with a certain probability of success will look like this. Okay, so for example, if I toss 15 coins and the probability of heads is 0.5, so basically it's a fair coin, right? I will see 15, what's half of 15? It's about around 7 and 8, right? So I see the bulk of the heads between 7 and 8 heads. There are rare cases, few cases in which I see 12, 13 or 14 heads or 15. There are rare cases in which I see say between 4, 3, 2, 1, or no heads at all, right? So this is how the distribution behaves. Now, if the coin is not fair, excuse me, for example, the probability of heads is only 20%, so it always falls on tails. This curve is skewed. Okay, it's not the bell-shaped curve that you saw earlier, but it's skewed. And it is likely that I will see in this 15 coin tosses somewhere in the vicinity of 2, 3, or 4 heads only, for the most part. It is going to be very rare that I see 7 or 8 heads, okay, because the probability of heads is lower. This is how coin tosses behave. Now, with this in mind, we will see that there are formulas to compute, say, for example, well, what's the probability of heads if the probability of heads is 0.2 and I don't know, I have 15 coin tosses or 100 coin tosses. Well, what's the probability that I see, for example, 7 heads? There are formulas to compute that, and we're going to use them. So let's go back to our example. So the 5 rounds of 10 coin tosses, so I just did 10 coin, I picked randomly a coin without knowing this time, without knowing which coin it was, and I tossed it 10 times, right? And for example, the first time I picked a coin and I tossed it, it yielded this number of heads and tails, right? The second time it yielded the rest, and so on and so forth. So if that's let's say that's the case now, and I absolutely made up, that coin A will have 60% chance of heads and coin B will have 55% chance of tails. So this is wrong. This should be a little 55, not a 5. Now, these are the tosses, right? So for each coin, these are my 10 tosses. For each coin that I picked, coin A and B, I don't know which one of these was coin A, was coin B, but I just saw the data. Basically, this is saying I have my patient data, I have my buyer data, but I don't know which marketing campaign, I don't know which treatment. Okay, and also I don't know what's the mean ratio of success for the treatment, for the marketing campaign, for the coin toss. So I just made up these two. Now let's take the first round, this one, the round number 1. There's 5 heads and 5 tails, so the proportion is 5 over 10 heads and 5 over 10 tails. Now we'll compute the likelihood that it was from coin A and coin B using the binomial distribution. Okay, so to compute the likelihood, let me go back to this graph, for example. Okay, in this graph, if I find, for example, let's say my coin has 50% chance. If I find 5 heads, so here, 5 heads, well, what is the probability? Well, the question is, what is the probability that these 5 heads came from a coin that behaves like this, as opposed to, for example, a coin that behaves like this, right? Where most of the times it will produce 5 heads, right? So what's the probability that I found 5 heads in a coin, in a fair coin, for example, in 10 tosses of a fair coin? That is what I need to ask myself. And then with the probability of 0.6, what's the probability that I found 5 heads in a coin that behaves like a coin that has a probability of 0.6? And for that, there's a little formula here, which is the binomial distribution probability, okay? And the idea here is that this formula will give us, if my coin has probability theta on n trails, on, in this case 10 trails, with k successes, that's the number of heads, right, 5, this is the probability that these k successes came from a coin with this probability. Okay? And the question is, well, what's the probability that it came from coin A and what's the probability that it came from coin B, right? And the one that has the higher probability so far is the most likely coin to have been picked. That's the idea. So now we move down. So we have, let's compute these things. So because, oh, by the way, a little math here. Because this term here is constant, I'm going to ignore it, okay? Because it won't affect the computation. It will affect the computation, but it won't affect which one's bigger, which one's lower, and it won't affect the step that I want to do next. So we have, recapping, my invented mean of 0.6 and my invented mean of 0.5 for the other coin. It was 0.5, not 0.55. So we take the first round with 5/10 heads and 5/10 tails. We'll compute the likelihood of coming from coin A using this formula, okay? And H now stands for heads. And that gives us 0.00079, okay, or 8. And the likelihood of coin B is 0.000976, so 0.001 mostly, right? Now, right now we can say that it's more likely to have come from coin B, which is correct, right, than from coin A. But the thing is that we now, because we only have 2 coins, we need to convert this into probabilities. These likelihoods, we need to convert them into probabilities. So what we do is we add these 2 numbers, right? And then we divide this guy by the sum, and then we divide this guy by the sum. And we get 0.45 for A and 0.55 for B. This procedure is called normalization. Okay? Again, take the sum of these 2, that's going to give you a number, and then divide this first number by that sum and this second number by that sum. If you divide the first number by that sum, you're going to get 0.45. If you divide the second number by the sum, you're going to get 0.55. Okay? And this is the probability that the first 10 coins came from A and that the first 10 coins came from B, given this means that I gave, right? And it makes sense. If it had 5 tails and B has 50% of success, well, it looks like it hit the mark for B, right? And not quite for A. This is what these probabilities are saying. So we're going to do this for all coin tosses, okay? We're going to do this for all of our trials, for all of our 5 trials. Now, let's recap. The probability that the first round came from coin A was 0.45. The probability that came from coin B was 0.55. Now, let's estimate the likely number of heads and tails from those different coins. So from coin A, the likely number of heads, or the estimated number of heads, is 0.45, which is, the likelihood that it came from coin A, times the actual number of heads, right? That gives you 2.2 heads. So if this had came from coin A, then I should have seen 2.2 heads. Now, and tails is 2.2 tails, because it's the same, basically it's the same computation. Now, if it came from coin B, then I multiply this proportion by 5 heads, which is what I saw, and that gives me 2.8 and 2.8 tails. I will tally these numbers, and I will do this for all 5 runs. And I will end up with something like this. These are my cases. Then for the first case, I got 0.45 times the likelihood that times my belief that it's from coin A, and 0.55 times my belief that it was from coin B. I got from coin A 2.2 heads and 2.2 tails, and I got from coin B 2.8 heads and 2.8 tails. Okay, I did this for all 5 tosses, and I got these numbers here. Then I add these numbers, the numbers of heads. I add the number of tails for each coin, and I get for coin A 21.3 heads and 8.6 tails, and here I get 11.7 heads and 8.4 tails. And what I will do is, with these numbers, I will compute the new theta, the new means for these coins. So for example, for the first coin, and I'm going to use this formula, the number of heads divided by the number of heads plus tails. So for example, for the first number there, for the first coin, for coin A, I will add 21.3 plus 8.6, and that's going to go in the lower bottom of the fraction, right? So, and that 21.3 and 8.6, that is basically 29.9. And the number of heads here, which is 21.3, I'm going to divide the number of heads by the number of tail, by the sum of heads and tails. I will do the same for coin B, and this will give me the new thetas for the coins. See, 21.3 divided by the sum 21.3 plus 8.6. So these numbers here come from these numbers here. Okay. I just want to point out, but I'm covering them. Okay. And that gives you 0.71. If you do the same for coin B, you get the new theta of 0.58. Now with these new thetas, this will be put in place of this, right? And this number will go in place of this one. You see how the thetas now are changing slightly. And then I'll go over the whole thing again. I will again compute the probability using the binomial formula, the probability that it came from these, that each of these runs came from coin A and coin B. I will compute the weights in absolute probability terms. I will register the number of heads, the expected number of heads and the expected number of tails for coin A and B, and I will compute a new mean, and so on and so forth. I will do this cycle many times until the computation of means don't change. At some point they settle, okay, or they start changing, in the 5th decimal, which you don't really care too much, right? Well, long story short, these coins settle. These coins will settle with these means: 0.52 for coin B and 0.80 for coin A. So coin A is going to be pretty skewed. Okay, so once you have the means, right? Once you have the means, then again, computing doing this step, right? The estimation step. Okay, you will see whether this first run is more likely to have come from coin A or B, and so on and so forth. Okay, and you can determine, using expectation maximization, you can determine whether the data that you see came from coin A or coin B, and what is the mean probability of success for the first condition and the second condition, or the first coin and the second coin. And that is basically estimation maximization.